Around 1895, autumn. A small town in Switzerland, Aarau. A 16-year-old boy stared out the window. Albert Einstein. A strange question formed in his mind. If I ran at the speed of light, what would I see? That question changed his life. At the time, Maxwell's theory had established light as an electromagnetic wave, and the prevailing view assumed ether as the medium of propagation. But Einstein had doubts. If he ran at the speed of light, the light wave should appear stationary. But no one had ever seen a stationary light wave. Something inside him began to crumble. The common sense of physics contradicted itself. Was ether theory wrong? Or did the speed of light hold some special meaning? The 16-year-old boy didn't have the answer. But this question stayed with him. Eventually, it became one of the crucial insights that led to the special theory of relativity in 1905. 1905, spring. Bern. 26-year-old Einstein worked at the patent office. Days spent examining patent applications. Nights devoted to physics research. And then, a moment arrived. The answer to the 16-year-old's question was found. Time is not absolute. The flow of time changes depending on the observer's state of motion. As relative velocity approaches light speed, a moving clock appears to run slower from a stationary frame. This was the special theory of relativity. June 30th, 1905. He completed his paper on the electrodynamics of moving bodies. The paper used minimal advanced mathematics, but built its argument at the core through both transformation equations and thought experiments. A train traveling at the speed of light. Two observers at different locations watching lightning strike. Through pure thought and logic, he grasped the essence of the universe. But Einstein didn't stop there. In 1907, he confronted a new question. What is gravity? Newton had said, gravity is a force that attracts objects to each other. But Einstein had doubts. One day, he performed a thought experiment. If an elevator were in free fall, what would the person inside feel? The answer was obvious. Weightlessness. Gravity hadn't disappeared. But for the falling person, gravity ceased to exist. In that moment, he realized, inside a small box, gravity and acceleration are indistinguishable. This was the equivalence principle. And from this principle, a stunning conclusion emerged. In general relativity, a freely falling object isn't subject to the force of gravity, so much as it moves naturally through curved spacetime. But expressing this theory mathematically was far from easy. For 8 years, Einstein struggled. Ordinary geometry couldn't describe curved space. He had to learn new mathematics called Riemannian geometry. Again and again, he hit dead ends. Again and again, he made mistakes. November 1915. Through successive lectures, he continued revising the equations, presenting the final form of the field equations on November 25th. Run shown half a gram mon r equals 8 pi g bar c to the power of 4 tun. This equation described the structure of the universe. Matter curves space. Curved space determines the motion of matter. This was the general theory of relativity. He stared out the window. The streets of Berlin slept quietly. 8 years of struggle had ended. The question a 16-year-old boy asked. The answer a 26-year-old man found. The theory a 36-year-old professor completed. Through pure thought alone, he unlocked the essence of the universe. May 29th, 1919. Principe Island, off the west coast of Africa. British astronomer Arthur Eddington observed a solar eclipse. According to general relativity, the sun's gravity should curve space and bend starlight. Eddington developed the photographic plates and measured. The observations were widely reported as supporting relativity. Though the errors at the time were large, modern methods, including radio observations, have confirmed light deflection with high precision through multiple approaches. November 6, 1919. The Royal Society, London. Eddington announced the results. They support Einstein's theory. In that moment, the world changed. The next day, the Times of London reported, "Scientific revolution, new theory of the universe, Newtonian concepts overthrown." Einstein became a worldwide celebrity overnight. A 16-year-old boy's question became a 36-year-old professor's discovery and changed the world at 40. But Einstein's thought experiments were far from over. 1935. Institute for Advanced Study, Princeton. 56-year-old Einstein confronted a new question. Is quantum mechanics correct? At the time, quantum mechanics was cutting-edge physics. But Einstein couldn't accept it. He performed a thought experiment. Two particles exist far apart. Measure one, and the other is instantly affected. Quantum mechanics predicted this. But Einstein questioned, how can information travel instantaneously? Communication faster than light should be impossible. This was the EPR paradox. Einstein resisted the probabilistic interpretation of quantum mechanics, and in a letter to his friend Max Born, he once stated, God does not play dice. Quantum mechanics describes the world with probabilities. But Einstein believed, the universe has a hidden order. We simply don't know it yet. That conviction he held until the end. In his later years, Einstein pursued unified field theory. He tried to explain gravity and electromagnetism with a single theory, but it was never completed. April 18, 1955. At 76, he passed from this world. On his desk lay unfinished equations, but the story continued. In 1964, physicist John Bell formulated the EPR paradox in a form that could be experimentally tested. Subsequently, from the 1970s through the 1980s, experiments were conducted to verify this theory. The results were astonishing. At minimum, the prospect that it could be explained by local hidden variables was strongly refuted by experiment. Verification advanced from the 1970s, reinforced by decisive loophole-free experiments in 2015. However, this doesn't mean faster-than-light communication is possible. Quantum entanglement shows correlations that cannot be explained by local realism. And EPR's challenge was a crucial move toward grasping the essence of quantum mechanics. For the achievement of this verification experiment, the Nobel Prize in Physics was awarded in 2022. The phenomenon Einstein called spooky is now scientifically proven and celebrated. Einstein's error became a monument of modern physics. And today, quantum entanglement forms the foundation of quantum computers. Even wrong questions can advance science. The power of thought experiments was that formidable. In 1922, Einstein received the 1921 Nobel Prize in Physics. But the citation wasn't for relativity. It was for explaining the photoelectric effect, his light quantum hypothesis. Ironically, the photoelectric effect became the foundation of quantum mechanics. He himself laid the groundwork for the theory he doubted his entire life. The journey that began with thought experiments was thus etched into the history of science. And today, humanity has succeeded in photographing black holes. In 2019 and 2022, the Event Horizon Telescope captured black holes in the M87 galaxy and the Milky Way. Their form was exactly as his equations predicted. A thought experiment from 100 years ago remains unshaken by the most advanced technology of today. Einstein once said, "Imagination is more important than knowledge." A 16-year-old boy imagined running at the speed of light. A 26-year-old man discovered the relativity of time. A 28-year-old man imagined an elevator in free fall. A 36-year-old professor unlocked the curvature of space. A 56-year-old scholar challenged the mysteries of quantum mechanics. Without mathematics or experimental apparatus, through pure thought, he grasped the essence of the universe. Now, I ask you, is the weapon of thought experiments still valid today? Can pure thought alone reach truth, without complex equations or expensive experimental equipment? Einstein's legacy is not the discoveries themselves. It's the courage to think, to question common sense, imagine the impossible, and keep asking about essence. Perhaps an undiscovered universe still sleeps within you. Share your thoughts in the comments. Thank you for joining me on this journey. Einstein's thought experiments are a universal method applicable not just to physics, but to every field. On this channel, we explore the thought processes and strategic decisions of giants, extracting wisdom we can apply in our own lives. If today's story inspired you, consider subscribing and leaving a like. And in the comments, share your own thought experiments. I'll see you in the next story.